Now let's start talking about programming your overlays. This first video will primarily talk about programming the new 14-bit macros, but to start off, let's just summarize what you will typically need to create your overlay. Well, of course, first you need some kind of graphic user interface that's capable of supporting the overlay functions that you want to provide for your application. This, in my case, could be using the Electra 1 MIDI controller that has that nice graphic interface. It could be using a Max MSP program, maybe SynthEdit, or maybe something running on an iPad that has a programming capability to interface with a MIDI application. That's totally up to you. So you need to have something to create a user interface, and then most importantly, from the programming end, you need a MIDI library capable of supporting a number of things. And if you don't have one, try and find one, or you'll have to create one on your own. The first thing that you'll need to do is send the standard 7-bit CCs that we've been using all along. But you probably won't be using too many of those, maybe 10 to 12 of the standard ones that support stuff like pre-gain, post-gain, recirculator maybe, but even there we can use the new 14-bit macros. Most importantly, you're going to need to send an arbitrary sequence of CCs. Sending a CC86 or a CC97 value with some other CC that maps to one of the 14-bit macros. In addition to sending CCs, you also are going to have to send poly aftertouch messages to support a number of other functions. Now, with just those few things, you can create an overlay interface that can do a lot of things as a simple controller. In other words, sending data to the EaganMatrix as the target and not reading anything back or processing anything returned over the MIDI stream. But to create a fully functional, sophisticated overlay, you're probably going to want to also read some MIDI coming back from the EaganMatrix and do something with it. And for that, you'll need to read some asynchronous MIDI I/O streams that are going to be sent back, primarily a stream of these poly aftertouch messages, but maybe some other CC messages as well. And then you're going to want to trigger some internal functions in your application based on what you've read. For example, maybe you want to read all of the system presets and put them up in a little menu. For that, you're going to have to read these MIDI streams. Then you'll want to have some general purpose I/O interface to read and write to your Continuum Mini EaganMatrix or Osmos device. Or you might want to also do normal I/O operations. You might, for example, want to read and write back a configuration file that you store your parameters in. So every time you run your overlay, you can store internally all your synth configurations that a user might create. And then, of course, there's other just general purpose interfaces that you think you might require. So that's the general requirement. Now, the next thing we want to do is just think about what this 14-bit macro means to us. As we said in the last video, depending upon how you interpret this 14-bit value, and a 14-bit value can go from 0 to 16383. Now, depending upon how you interpret that, whether you use a bipolar macro or a unipolar macro, internally in the EaganMatrix, it's going to scale to two different sets of values. For the bipolar, that 0 to 16383 will scale -1 to 1. For the unipolar, that range will scale 0 to 1. So obviously, if you only want to use positive values, you're going to get twice your resolution on the unipolar macros. However, the controller that you're using, perhaps it's a dial or a slider or something like that, it might not be able to accurately support that many bits of resolution, or it might be very difficult for you to move things so slightly that you can accurately use that resolution. Our 14-bit value on the left here probably in your application is not going to be a 14-bit word. It'll probably be a 16-bit word, or maybe even a 32-bit word, or maybe you somehow have something that's using two 8-bit entities that you're aggregating, but probably you'll be using a 16-bit word. Let's use that as the example here. Obviously, for a 14-bit value, we're not going to use the highest 2 bits in a 16-bit word, but remember, we have to split up our 14-bit value into an MSB and an LSB part. Each of these is going to map to a CC. CCs in MIDI, we're using the MIDI 1.0 spec here, are only 7 bits. So we're going to have to, in our program, take this 14-bit entity and split it up into the correct most significant and least significant parts. In our table here, you can see going -1 to 1 for our 14-bit values. If I have a 14-bit value of 0, that's going to map to -1 in my bipolar macro. That'll map to 0 in the unipolar. Let's say I go to value 4096. That's half the way to 8192, which is going to be 0 in the bipolar macro, because 8192 is half of the max value, and it will be 0.5 in the unipolar macro. In reality, 16384 would be the actual 1.0, but we're only talking about two 7-bit CC entities. You can't go to 15 bits, which is what 16384 would be. So the EaganMatrix scales this 16383 value as its max 1.0 value. Then, of course, if I add another 4096 on the 8192, that will take me to 0.5 bipolar and 0.75 unipolar. And in both cases, if I go to the max 16383, that's going to map to 1 in both unipolar and bipolar cases. So now comes the fun part, and that's how do you program this? Well, fortunately, in my case, for the Electra 1, there's a pretty sophisticated MIDI library that comes with the Lua programming environment that you can use there. I've created a number of functions to create my 14-bit macro, so I can do it a couple ways. I've created one that sends a CC86 value macro and another one that sends a CC97 value macro. I could create another routine that's more generic and have one of the input arguments be the CC86 or CC97. That's all up to you how you want to program this. But the main thing is that if you're sending in a 14-bit value, you'll need to take that value, if it's a 16-bit integer, for example, and shift the 7 bits of the MSB over so that you can create your 7-bit MSB value. And then on the original 16-bit value, you're going to want to mask off the bottom 7 bits so that you can create your least significant 7-bit value from that. I did that in this simple function. So I've sent in my 14-bit value. I've split it off into its MSB and LSB parts, each one of which is 7 bits. And then I have, fortunately, in my Lua MIDI library, a function send control change. And that takes a device port, which would be my either USB port or my DIN port in this case. It takes a device channel. That's going to be channel 1 for us sending the macros. And then it takes a CC and the value of that CC. To send the 14-bit value, you will first send your CC86 with whatever the LSB value is for that. And then you'll send your CC, whatever it is. Let's say it's CC40 if you used macro 7. So you'd send a 40 in there, and then you'd send whatever the value of your MSB part of your 14-bit value is. So here I've used a more generic function. In this case, I add the parameter that I'll send either CC86 or CC97 in on, and then I'll send my LSB, and then I'll send my MSB. Now it's up to me to track and make sure I'm sending in the desired value for either the unipolar or the bipolar macro. So in the case of macro 7 here, that's going to be a bipolar macro. I'll make sure I send in my CC value that I want that maps to the macro, and I'll make sure that the value I send in is appropriate for what I want to do. If I have something that takes a positive value on this macro, I'm going to want to make sure that the minimum value I send in is 8192, which will be 0. If I use a unipolar macro, in that case, I'll use CC86. All the unipolar macros use CC86. I'll send in the right macro I want. CC12 maps to the first unipolar macro, and then I'll send in whatever the value I need, and my routine will, as we saw, split that up into its LSB and MSB components. Now maybe in my program I don't want to work internally with 14-bit integer values. Maybe I want to work internally with values that are scaled 0 to 1. I still need to send to the macro, however, the 14-bit value. So in this case, I can create a routine that first takes my value 0 to 1 and then scales it to a 14-bit value that I'm expecting. In this case, I'll add 8192 because this is going to assume I'm only scaling a positive value. Perhaps I want to work in values -1 to 1. Well, in that case, if the value is less than 0, then I'll scale it accordingly by subtracting the percentage of my value in relationship to 8192 from 8192 to get me that value between 0 and 8192. And then, of course, anything from 0 onwards will be the same scaling I had before. Well, let's look at a preset and see how we're going to map these. I have a simple oscillator using X as its frequency and 3 formulas. I'm going to output the oscillator to SLSR, and if I look at that formula, I use a W scaler on my Z with macro M7. Now when you first come into the editor, your W will look like this, just a constant default. For you to create the macro, you'll go and select macro. Note you can also scale the macros 1 to 127 as in the original macros, but you'll probably not use that nearly as much as the normal 0 to 1 scaled macro. So once I select my macro option, a fourth control dot appears. You can select that and then select any of your macros, your unipolar 1 to 6 or your bipolar M7 to M90. We'll just select M7 here. So as I change in my overlay M7, I will in effect reduce the scaling value on my Z. And if, for example, I set M7 to a 0.5 value, well then that's going to scale my value here to 0.5, and that's one way to control your Z scaling. Again, remember, if I set this to 14-bit 0, this is going to set W to -1. Now, in the case of output amplitude, that might be okay, but in other cases, it will not. I might point out that you can also scale Z directly with a macro. So scaling this way would do a similar thing. I can, in my overlay, control M7, and if that M7 is set to only go to 50% of the 14-bit range for the bipolar macro, and so if that macro is set to send in 12288, or the value that will map to 0.5 on the bipolar scale, the maximum value of Z then would be 0.5. So we'll take things back. Now, I've created a frequency offset that goes to 0.1, and that uses my standard macro 1, which I'm going to apply as a 14-bit unipolar macro. Here, that will allow me to create very fine frequency offsets in the 0 to 100 Hertz range. Finally, I have a formula on my spectral balance, my timbre for this oscillator, and that I'm controlling by Y, a shelved Y in this case, and I put M49 on that. That's one of the CC97 macros. The CC86 macros end at M48. So as I change my M49 macro value, that will limit the maximum value that Y can take. And if I set M49 to 0, 8192, in this case, because it's bipolar, that means that Y will never be able to be set past 0. Remember, applying macros to X, Y, and Z will scale those to a max or min value for your macro. Let's end with a short practical example using the Electro 1 Lua programming interface and the user interface builder that comes with it. So I've created for my oscillator preset that we just discussed 3 controls: a bipolar level control, a unipolar detune control, and the bipolar timbre control that will be Y based. In this interface, I can just select the graphic object to bring over, and then I can assign a callback to it. In this case, I'm going to set the 14-bit 86 base macro for the level. For the detune, I'm going to set the same thing. And because the timbre is using a higher CC, I changed that to a macro 50 from macro 49. That'll use a CC97 based callback that I have created here. This interface lets you do standard CC stuff, but because these are all non-standard 14-bit CC control values that we're using, I set this so that it's not going to try and use any internal typing or message. It will use the callback function that I've defined for this. The CC that'll be assigned for macro 7 is 40, so I'll set that to the 40 parameter here. The detune is using the macro 1 unipolar macro. That's parameter 12 that I'll set here. And you can see this also lets me set a min and a max value that will be sent out. Because I don't want my bipolar value to go negative, I'll start at 8192 as min value to the max 16383 for the level. For the detune, that's unipolar, so I'm going to give the full range on that 0 to 16383. And the timbre is also a bipolar macro that will start at 0, so I'll range that one 8192 to 1683. There's some formatting functions, callbacks I can create to set the output of these things to a representative range value. Instead of saying 8192 to 16383, for example, this formatter, the way I have it, will output a 0 to 1 floating point display. Then I can go in to the programming, and this was done for something that needed a lot more programming, but I have my function set 14W86. This is similar to what we used before, only it uses some internal values that are generic to the user interface. So it'll take in the value, it'll shift it for MSB, it'll mask it for LSB, and then I'll get the parameter as well for the CC, and I'll make sure that that's mapped to an integer. And then I will send my 2 messages that we talked about, the CC86 LSB message, and then I'll send the CC40 in the case of the amplitude with the value that's set in the control. And that will allow me to manipulate the 14-bit macros with the Electro 1 user interface. And to end, we can bring up our preset, and let's click on A. That's our output amplitude. You can also look at the right here. I've turned on the display. If you hold down the fingerboard and play a note with display on, you'll see the current value of that. I'll play the Continue Mini that's hooked up here. I don't hear anything because I have the scaling on the level on Formula A set to 0. So M7 is 0. That means no matter what my Z value is, I won't get any sound. As I bring up my level, you can hear the sound comes in. So the max Z will be scaled to whatever my level is here. And you can see the value changing in the display on the screen. So that macro is being sent from my Electro One overlay interface to actually an EaganMatrix module that's running this preset that's controlled by the Continue Mini. I could have run this directly on the Continue Mini, of course, but I already had things set up this way. Now, let's bring up the detune. You can hear as I bring that up, I'm increasing the frequency. I'm adding a frequency offset up to 100 Hertz. If I click on B here, you'll be able to see the formula display changing there as well. And finally, let me turn up my timbre control. I'll press the very bottom of Y. There, let me turn up the timbre. You don't hear anything? Because this is Y controlled, remember. So as I play up on Y on the Continue Mini, you'll hear that timbre kicking in. If I make that timbre value very low, you'll hear less of a timbre change. As I turn it up higher, the spectral bounce will get to a higher value, and you'll be able to hear that Y change. And all of these are dynamically changeable with my Electro One controls. That's how overlays work. Of course, this is the simplest of examples. The ones that I've been showing you up to this point are a lot more complicated. But in terms of just basic 14-bit macro control, this is what you have to do. And with just this, you can create some pretty sophisticated overlays for just controlling your preset without having to worry about reading anything back and doing any of the more complex overlay operations. But we're going to start talking about those next.